Tycho Brahe was one of the extremely interesting characters that were associated historically with the astronomy. What you can see over here is the Tycho shown without a piece of his nose and with this kind of a copper prosthetics. And in the background, you see this elk, which was his best buddy, and he was also his drinking buddy. You can read more about that on Wikipedia or in my lecture slides. In the background, you see basically this starry sky, and Tycho Brahe is actually credited to be the best naked eye astronomer. What you see over here in this second picture on the first slide is the observatory that Tycho had a Danish king build for him. Tycho was very fortunate that he was a pretty rich guy and he was very close to the king and the queen, and so he had the king build him this observatory that he called Uraniborg, or the castle of Urania. Urania is the muse of astronomy. So in his observatory, Tycho was very disciplined. Night after night, for years, he observed very diligently the sky and the positions of celestial objects. The stars would not change their position, but Tycho was very specific in following the positions of the planet. And remember how it was a really big mystery to Greeks why planets exhibit those retrograde motion. So what you see over here is the Tycho sitting. This is the instrument that he had. Remember, this is the time before telescopes. So he does not have telescopes. The only instruments that he have are kind of these medieval looking things that basically measure the angular position of the object on the sky. He looks through this hole over here. He sees the celestial object. He reads out over here the angular position of that, and the assistant over here records that. This is one of the instruments, how it looked like, and as you see, basically it was a very high accuracy object that measured very precisely the position of the objects. So believe it or not, Tycho was able to basically write down and to track all of these celestial objects with a precision less than the thickness of your fingernail viewed at the arm's length. So that is kind of as good as it gets even at these days if you're not using the telescopes. Okay, so he was very well equipped, but then also he lived in some really fortunate times when many interesting things happens basically in the skies. For example, in 1572 he was able to observe a supernova explosion. These are associated with the deaths of the massive stars, and this actually, so it what he's seen on the celestial sphere is as if the new star had appeared out of nowhere, right? Which kind of contradicted the Aristotelian assumptions that the celestial sphere never changes. And not just that it appeared for one day, but people could see actually the supernova explosion for 18 months. It was kind of a visible and fading away. In addition, Tycho has witnessed this great comet of 1577, and this was something that was visible during at sky actually, or in sky during the day and the night time. Very big object. So you can even see it over here, kind of depicted in this piece of art. And over here you see these drawings by Tycho of the comet. Now, Tycho was very smart and he reasoned the following things actually. Both imagine how do you know actually that this supernova or the comet are not really close to the Earth and they don't belong to the celestial sphere? Well, he was able to reason why both of these are very, very distant and belong to the realm of celestial sphere. Imagine that either one was kind of a really close to the Earth, maybe like at the moon's distance. So if I had over here that supernova explosion that happened or the comet, if you look at two people on the Earth at different locations, right? And if they look actually both of these different, let's say, persons on the earth at different locations, see over here separated by the distance d, then one looking would see basically this object in this constellations over here or near this star. The other one that is kind of a little bit more to the north, looking at the moon, would see it kind of a projected a little bit less or towards the south over here. So this is what he considered to be a parallax as well of this object, and because he could not measure the parallax of either the supernova explosions or of the comet, he was very confident that that object belonged to the celestial sphere. However, he also tried to measure the parallax of the distant stars and could not succeed in that, the same like the Greeks could not. So he actually left, in his view of the solar system, he left the Earth as stationary over here in the center. The moon went around the Earth, the sun went around the Earth, but then everything else went or revolved around the sun. So you can imagine that this model got ridiculed by many people, and many people made fun of Tycho Brahe. And so what he did actually during his lifetime, he heard of a very young boy, Johann Kepler, who lived in Germany, and who was kind of a very well known by his math ability or mathematical ability. So Brahe Kepler traveled to Germany to find this little man or young man. And so he met him and he met his parents, and he made an offer to his parents. He said, because they were actually a very poor family, they had a lot of kids, they lived like peasants in the village. They basically were just like in the agricultural kind of a business. So he offered them actually that he would take Kepler, that he would take his son, their son, with him. He will pay for his education. And also, actually, while he's taking kind of a Kepler away from the fields and the manual labor, he will actually pay to the family to hire a person to help them out in the field work. So parents thought that this was like a pretty good deal for them, very generous offer. So they gave their son actually to Tycho, and Tycho took Kepler, did whatever he promised to do, and so Kepler became actually a student of Tycho Brahe. Carl Sagan famously said that the Johann Kepler is the first astrophysicist and the last scientific astrologer. Supposedly, when Tycho was dying, kind of on his deathbed, he was begging Kepler to work with the data that he collected over the last 20 years and to give some meaning to that data so that he did not live in vain. He felt really bad that basically people made fun of him and his model, and he asked Kepler if he can do anything with that data. And obviously, because we call him the first astrophysicist, Kepler was able to make sense out of that data. So over here you see Kepler, you see his drawings over here related to his three laws of planetary motion, and here is Tycho Brahe in the portrait next to the Kepler. So what Kepler did actually, because he has these long-term observations of the Mars and its orbit, he started plotted those points for the Mars, and he actually noticed that he believed in this data that Tycho collected, and he knew that they were done with unprecedented accuracy. He noticed that the orbit of Mars actually is not really circular, but it actually had a little discrepancy. It was a little bit off from the circle. So first, Kepler's conclusion was that the planetary orbits are not ellipses, but that they're not circles, but that they are ellipses. Now we go back to our UNL website. This is Planetary Orbit Simulator, and over here you have different options for the Kepler's first law, second, third, and then some Newtonian features. We are going to leave that for the next week. Now, if you look over here, this is the circle. So the circle is actually an ellipse that has eccentricity. This parameter over here, eccentricity, is important, of 0. Circle is the ellipse with the eccentricity 0. If I actually go now and increase this eccentricity, what you notice actually, right, is that this is now becoming less and less and less circular. And you notice something over here called the empty focus. So I'm going to put this back to the circle. I'm going to click over here, show center, show semi-minor axis, and then show semi-major axis. If you think about the circle, there is no difference between semi-minor axis and semi-major axis. Those are simply the radius for the circle. But as this departures from the circle and becomes more oval, right, what you see actually is that there will be a difference between semi-major axis, this is the longer axis, and the semi-minor axis. So these are two characteristics that we use basically to describe the motion of the planet. The semi-major axis gives you the average distance from the planet, from the sun. Now notice that the ellipse has a center. like the circle as well. But that center is not relevant for anything. There is nothing in the center. The ellipse has two focal points. In one focus we have sun, the other focus is empty. So as you go back actually, and I'm gonna make this almost to be like the Earth's orbit, right? You see how these focal points come closer together and they come closer and closer to the center. The Earth's orbit has this kind of eccentricity, approximately point like 2. So this is the Earth's orbit. As you see, this really departs just a little bit from the circle. The focus, the one focal point where the sun is very close to the center, and also the empty focus is just over here. So this is the ellipse for you. It's an oval shape that we call. It does not have a center, but it has two focal points, and sun is in one focus, the other focus is empty. Now, if we start this planet moving, right, what you will notice that at some points the planet goes further from the sun, and at some points the planet comes closer. And if you actually play with this eccentricity, made it more eccentric, you will also notice that the planet will change its speed, right? And then basically that the planet will slow down. Here are the radial lines. You can use this, right? And so you can notice, actually, I'm going to pause this now. This line that joins the sun and the planet will be very important for us in the second Kepler's law. Because when the Kepler worked, there was no calculus. He mostly relied on the geometry. So here we come to the Kepler's second law. I'm going to click over here. I'm going to now reset all of this. I'm going to erase. And then I'm going to do something over here. Sweep continuously. Start sweeping. And what you see now over here is how this planet goes. And you can imagine, right, that there is this line that connects the planet, right, over here. Imagine this line connects the planet with the sun, and as the planet moves, right, that line is sweeping these areas over here. So now pay attention to this green area and this blue area. They are the same areas. So if you were to calculate this area, which is approximately triangular area, those would be the same. And they're only going to be the same if the time that it takes planet to travel from here to here is the same as the time that it takes planet to travel from here to here. Now let's compare something that is more extreme. For example, when the planet is over here, farthest out, it tells you if, let's say, from here to here along this golden arc is 1 day for me. And this is the area that line that connects the planet and the star has swept in that 1 day. Then if I go over here when the planet comes really close, and if from here to here is 1 day, then this blue area will be the same as this golden area. And if these two areas are the same, the time that it took planet to travel is the same. So if that's correct, this is much less of the path that the planet travels. The planet travels along the ellipse. This is much shorter than the path over here. But it's done in the same amount of time, which tells you basically that the planet, when it's closer to the sun, moves much faster than the planet when it's farthest out. And so the Kepler's second law is formulated in kind of a way that it's not that intuitive, but it tells you that this line that joins a planet and the sun sweeps out equal areas in equal intervals of time. So once again, if the time from A to B is 1 day and time from C to D is 1 day, then these two areas are the same. And so why this is formulated this way? Simply because Kepler, the math that he had at his disposal was mostly arithmetic and the geometry. He did not with the calculus or didn't deal with the calculus or anything basically that has a higher precision, simply because that was not yet invented. As a consequence of this law, when the planet is closer to the sun, as you've seen, it will travel faster because it has more path to cover, and when the planet goes further out, it will slow down. So as you know, this is now challenging those Aristotelian views that the planet is a perfect circle or a perfect sphere moving on a perfect circle and never changes its speed. So Kepler was able to see that is not the case. Now over here, you can pause if you want. and do the first lecture tutorial. So the first part will be, the first page will be very simple, but on the second page, then you have to choose basically, you have something similar like this given, the planet will move from A to B and you will shade that area. And then you have to start from that point C on the second page and to see how far you need to go before the area that that line will sweep will match this area. And then you should derive some conclusions from over there. Finally, to formulate the Kepler's third law, we need to define some distance, distant unit that is very convenient for us for the solar system, and that is the astronomical unit. Astronomical unit is the average distance from Earth to the Sun, and it is measured to be some certain amount of the millions of miles or millions of kilometers. But for what is important for us is actually that average distance of the Earth from the Sun we call one astronomical unit. So Mercury and Venus, which are inner to our orbit, will have the average distance less than one astronomical unit, and Jupiter and Mars and Saturn, which are outer to our orbit, will have the distance, the average distance more than one astronomical unit. Okay, and so now if you know that average distance of the planet, this is the average distance of the planet or semi-major axis in astronomical unit, and if you know the time that it takes the planet to go around the sun, and this time is given in years, then if you square that time and you cube that distance, they should give you the same answer. So basically what this law does for us, the third Kepler's law, is the fact that Kepler kind of concluded from the data that closer the planet is to the sun, the less time it will take to go around the sun. And here is the data for our solar system. You see Mercury over here. It takes only a quarter of the year, or 3 months, to go around the Earth. That means to go around the sun. So that means 4 times during a year, Mercury will complete its revolution around the Sun, and for Earth, that will be only 1 time. If you take this time or this period expressed in year, you square that, and then you take the known distance of Mercury from the Sun, and you cube that, you get the same number over here. And so you can see and compare for all of the other planets, the same will hold. And so what third law tells you actually is what planets do on their specific orbits, or it compares the planets. The first Kepler's law was basically just about the orbits, the shape of the orbit. The second law was what a particular planet does on its own orbit. And the third law compares all of the planets and tells you closer the planet, the less time it will take to go around the sun. Also, what the third law tells you, and we are going to prove that next week when we do Newton, is that mass really does not matter. You will see why is that the case. But what you need to know so far is closer the planet to the sun, the less time it will take. So you can put two completely different planets on the same orbit around the sun, and they will actually take the same time to go around the sun. The bigger one, the chubbier one, right, will not take more time to go around the sun. As long as two objects have the same basically average distance from the sun, they will take the same amount of time. Okay, now that's all that we have for Kepler. You are ready now to do this third law, Kepler's third law. And after that, you can go to Galileo. Galileo is one of the very interesting scientists, one of the maybe like greatest scientists that ever lived. He, by education, was a mathematician, but then also he was a very kind of a diverse interest. He was very good in applied sciences and technology. He improved compass and he improved the telescope. Note that Galileo did not discover the telescope, but he actually improved the telescope. Telescope was discovered a few years earlier, but by two Dutch guys, and we are going to actually mention them when we talk about the telescopes. So now imagine Galileo having this telescope and pointing the telescope at skies. The kind of a completely new world opened for him, and he realized that the universe is much bigger than what we perceive universe to be, looking from the earth with our eyes. He pointed his telescope at the moon, and this is still one of the best sites that you can actually point your telescope at. The moon looks just like amazing when you look with a telescope. You can resolve all of these basically Marias or the flat regions of the moon. You can see craters, you can look at the shadows inside of these craters. And so he realized basically that the moon is not that perfect spherical object as what Aristotelian said. The moon is not a perfect sphere, but the moon, the same like the earth, has the mountains and the valleys and the seas that he thought were on the moon. Then he pointed his telescope at the sun, and you probably know that Galileo died as a blind person just because he was staring for a long time at the sun. And he also realized that the sun is not this perfectly smooth spherical object, but it has a lot of these blemishes that we call the sunspots, and that these sunspots actually they're not really stationary, but they move around the sun, revealing that the sun rotates. So Galileo was able to figure out that sun rotates, and also he was able to, by studying carefully these sunspots, figure out that this rotation is not uniform. It does not rotate as the solid body. We are going to talk about that more when we do sun. Finally, Galileo also observed Jupiter, and he was able to see four moons about Jupiter, and these four moons are called Galilean moons. Even with the binoculars, you can see these moons, and what is really interesting, like this innermost moon only takes 2 days basically to go around Jupiter. So if you look long enough, you will notice basically that these moons change their position with respect to Jupiter, and that is depicted over here in Galileo's data. So what he was able to conclude by looking at Jupiter moons is that the Earth is not unique, that it has its moon and it doesn't have that everything doesn't have to go around the Earth, because Jupiter actually is almost like a solar system in small. It has all of these moons that rotate around it or revolve around it. And so finally, the most important observation that Galileo did are the phases of the Venus, and we already mentioned this when we did Ptolemaic system. So what you see over here is that the Venus has all of the phases, and actually this is more visible over here. When the Venus is close between the Sun and the Earth, it's going to be new. When it's very far away from the Earth on the opposite side of the Sun, it is going to be full. From new to full, Venus changes size 6 times. So it's 6 times bigger over here around the new phase than when it is full. And Galileo was able to show that, showing basically that was one of the evidences that Venus does not go around the sun, around the Earth, because it would kind of keep the same similar size. But over here it was evident that Venus goes around the sun because its angular size changes 6 times. In addition, in Ptolemaic model, you could not have any other phases by the crescent phases, and Galileo was able to observe that Venus has all of the phases, the same like the moon. And so this was basically the most important evidence that Galileo collected against the geocentric model. Full phase gibbous phases of the Venus cannot be explained in that Ptolemaic system. Go back and review those animations and make sure that you understand. Interestingly, the Venus is actually going to be the brightest when it is in the crescent phase, and that is the combination of the size and the illumination of the Venus. Finally, Galileo also observed Saturn, but Saturn in a way was very confusing to him. What you see over here, sometimes he called it the being with the ears. He actually thought that Saturn had like 2 moons, but sometimes depending on the orientation of the Saturn, the moons would disappear. And so during his lifetime, Galileo was not really able to figure out what was the thing with the Saturn. He was not able to see its rings. The first person to do that will be Cassini, and that's why the first mission that we had dedicated to Saturn was named by Cassini. Okay, so that's all for this chapter. Next time we will do Newton, and that will end the mark of the second chapter. And after that, then you're ready for your first exam.